Okay, so this is another E-field question. The diagram shows a full-scale cross-section of the E-field in this region. Okay, so it's some weird shape, some rod U-shaped metal frame. Okay, but doesn't matter. So basically, this question is testing you on just potential and some conservation of energy as far as I have read through. Okay, so let's go through the answers for the question. Okay, so the potential difference now they tell you here is going to be 600 volts. I can see the equipotential lines. Okay, they start to go out here. Now all these are few lines, and that's where the first question is testing you. Okay, so on the figure, draw an arrow at point A to show the direction of the force exerted by the field on a small positive charge placed at point A. Now at point A, okay, this here, which is here. Now, what happens is that the direction of field lines is the direction of force or the positive charge. Okay, that's what it means. So in this case, it's a positive charge. So at A, the force of the positive charge will be at the tangent to this line, so it will be just towards this direction. So that will be part part A. Okay, the answer for part A. Basically, it will be a tangent to the line at that point. Okay, if it's an electron, it will be in the opposite direction. Okay. So on figure 1.1 also, draw a dotted line on the figure linking all the points where the potential is 150 volts. So basically, it should be between the 100 and 120. So we should go somewhere in between, estimated. Okay, so you should be somewhere in this manner. Okay, so you'll draw one full circle here just to show that that's all the points. It should pass through B. You can see B is just nice at the center. So B is also at 150 volts. Then you will go through here, aim around the center. Okay, that will be good enough. Okay, that will be between 100 and 100 and 200. Okay, so for part C now. For part C, I am not able to do it when it's on the computer. So just take note, you're supposed to take readings and measurements, which means that you need the actual diagram. So how we will be doing it is with the actual diagram is that we'll actually be okay, let me just zoom in here. Okay, you're supposed to determine the magnitude of the E field at B. Okay, where the field may be considered to be uniform. So now, if I zoom in, okay, all the way in at B, this is what happens. I will need to measure the distance between these 2 points. Okay, maybe I will just use a pen that's not so thick. I'll need the distance between these 2 points. Okay, measure with a ruler because you need to measure to scale. And we know that this is 100 volts. Okay, this one is the 100 volts. This one is the 200 volts. So when you measure D, the E field is just V over D. Okay, potential difference divided by D, and the potential difference is going to be 100 volts between these 2 points divided by D, and that will give you the E field here. Okay, it's just that I do not have the, I mean, probably on different papers, it can be quite difficult. I mean, it can be quite different, so I can't measure here, so this is just how it can be done. And next part, calculate the electric force acting on an electron placed at point B. So once you have the E field strength here, just F equals to QE. Okay, which is pretty simple. The charge of the electron, you already know is going to be 1.60 times 10 power minus 19 coulomb. So just F equals to QE. Okay. Next part. Calculate the work done by the E field, the E force, if a proton is moved from C to D. Now, from C to D, C, you can see that's going to be at 300 volts, and D is going to be at 100 volts. Okay. So the potential difference, okay, is going to be, let me just put here a bit thicker. The potential difference is going to be 200 volts. Okay, 300 to 100. So work done equals to QV. So 200 times 1.6 times 10 to the power of minus 19, which is the charge of the proton, okay, which is the same as the charge of the electron. So you just get 3.2 times 10 to the power of minus 17 joules. Okay, so it's pretty straightforward. And the last part, now an alpha particle, okay, mass proton and alpha particle are accelerated from rest. Calculate the ratio of the speed of proton to the speed of alpha particle. So now I hope you know that alpha particle is the nucleus of a helium atom. Okay, which means that it has 2 protons and 2 neutrons. So that's why the mass is 4m. Its charge is going to be due to the 2 protons, so it's twice the charge of the proton. So now, for point C to point D, so we already have the PD, we already have the KE of the proton, okay, because the proton, they are accelerated from rest, and this is the work done. Okay, work done is equals to QV. So for the alpha particle, same thing. For alpha particle, the work done, okay, is equals to 2QV. Okay, it's twice because it's double. Okay, so it will be 6.4 times 10 to the power of minus 17 joules. Now, the thing is that this work done goes in the KE. So what we need to do next is to compare the KE, then we can compare the speed. Okay, the question asks for the ratio of the speed of the proton to the speed of the alpha particle. So what we want is the KE of the proton over KE of alpha particle is equals to 3.2 divided by 6.4 is going to be half. Okay, so this continues that the half m v of proton square divided by half 4m v of alpha particle square is still half, okay, because that is ke of proton, ke of alpha particle. So from here it's quite obvious we are going to cancel this half here, we are going to cancel the m here. Okay, we are left with this 4. Okay, so this is just basic mathematics. Vp square over V alpha square is equals to, multiply is going to be 2. So Vp over V alpha, the ratio is going to be root 2 or 1.4. Okay, 1.414, but I put the 2 SF. Okay, so that is the answer here.